Hello and welcome to the continuation video for how dual PWM works, or how PWM works, but also dual PWM, because that's what we're going to talk about today as well. In the last episode, I said it was part 1 of 2. That was before I knew everything that I know now. So I am very sorry. There will be a part 3. Because otherwise this video would be so long. It is already so long. I'm recording this after I've done all the research and done all the video. And it's just so much stuff to cram in. So yeah, you're not going to sit through all that information. You will barely make it through this one, I think. But it's really interesting how this works. So in this video, we are going to speed up the PWM speed, and we're going to talk about the resistors thingy to get the levels right, so we actually get a smooth signal between the most significant bits and the least significant bits. Those state diagram things that we saw in the previous video. We're gonna see more of that in this video. And then we have to do the filter in another episode, hopefully not that, but there's all kinds of math for the filter design as well. So just to, yeah, it's a lot, but it's very interesting. Again, it's very useful, and if we get this right, and when we get this right, we will be able to use this for very nice analog signals. So that's why I want to get it right and learn as much as possible, and hopefully you too. So with all that said, thank you to my patrons who support me in this endeavor and are very patient, because they don't get much more information than you do, and all the information they've gotten this time is, this was difficult, I don't think I can do this in one video. So yeah, they just know that I'm working on it, I guess. But thank you so much for being on Patreon. It's super nice of you. And yeah, let's just get on with this video, because there's a lot to unpack here. You might also have quite a lot of questions during and after this video. Please leave them in the comments. I don't say that enough, but leave them in the comments so they stay with the video, and I will try to explain and clarify any information that I failed to communicate in this video. Let's begin by going through the 3 problems that we need to look at and solve today. First of all, the PWM speed, which is the biggest issue and the one that's going to take the longest time today. We have 3 pairs of PWM ports. So pin 3 and 11 is 1, pin 5 and 6 is 1, and pin 9 and 10 is 1. And they are connected to each other and controlled together as one. We'll go through that in a minute. The default speed is 490 Hertz for 2 of the ports, or pair of ports, and one has 980 Hertz. All this is within the audible range, which is not good for our purposes, and that's what we need to fix. We need to get this out of the audible range. The second problem we have is the ratio between the resistors in the voltage divider for the 2 PWM ports going out with dual PWM and the accuracy of the resistors. So we're going to talk about that. And finally, it is the filter. We need to filter the PWM signal we get here in a good way that gives us a nice steady voltage or audible signal. But let's start with the first problem with the PWM speed. As soon as you dive this deep into a specific part of a microcontroller, it becomes very microcontroller dependent. So we're just going to talk about the ATmega 328 today. And also you unfortunately need to consult the datasheet quite a lot. And I know as soon as the datasheet comes up in one of those videos, I usually zone out. So I'm not gonna have this in front too much. I might show a few things and instead hope that I got all the nuggets out of it here. So I'm gonna try to explain this in simple terms. So the ATmega328, first of all, it's got 3 timers. Timer 0, timer 1, and timer 2. And depending on how much you've worked with Arduino in the past, you have used these timers for different things. Important to know is that timer 0 is where millis and microseconds and all that, I believe the system clock is running on the timer 0. That's a technical way of saying if you can, leave the timer 0 and all these things down the line here alone as they are, because it might affect other parts of the Arduino sketch that you're working with. So these timers then have, each timer has a pair of output compare match outputs, they are called, and these can be set to a pin. So these output compare, so output compare 0, A and B, they are then basically pin 5 and 6. OC1 AB is 9, 10, and OC2 AB is 11 and 3. Those, so again, it's complicated, but they can be pins. They don't have to be pins. You assign them to pins in the timer counter control registers. So there's 2 registers for each timer, for each pair of output compare match outputs, and these are called TCCR 0, A and B, 1, A and B, and 2, A and B. And again, you see that 0 and 1, 2, 0, 1, 2, it goes all the way through. Important to know that OC0A is then correlates to the OCR0A down here. So A does not, the TCCR0A and B does not correlate or have anything to do with the A and B of the output compare ones. So these are just that you need two registers, two 8-bit registers to set all the bits that is needed to be set for all the functions for this PWM then. So then we have the pins, and the pins then correlate to the output compare if we connect them to pins. So OC0A is output pin 6, B is 5, OCR1A is 9, OCR1B is 10, OCR2B is 3, and OCR2A is 11. And if you heard, I added an R here, and that's because these are the output compare registers, and this is where you set the value of the PWM that you want in the register for the output compare. So then in the timer counter control registers, there is a bunch of different settings you can do. What these registers will end up doing is setting these two things for the PWM. We have the mode, first of all, the mode of the PWM. So we have fast PWM and we have phase correct PWM. And I will show you in a scope in a minute the difference between these. The fast PWM, so you have the timer that counts from 0 to 255, 8-bit timers. And this one counts up from 0 to 255, and then it resets and resets 255, resets 255, like so. Once you have the once you set a value to this OCR0B, for example, then the PWM signal goes high at 0, then it stays high until it reaches, the timer reaches the value of the set OCR0A that you've set, and then it goes low, stays low until it goes back to reset to 0, and then it goes high, and that's how you get the PWM signal. The second mode is phase correct PWM, where the timer counts from 0 to 255 and then from 255 down to 0 again, and then it goes like that. So the phase correct one, it stays low until it reaches the value you set in the OCR0A, for example. Then it goes high, and then it stays high until it starts counting down and reaches that same value again. Then it goes low, and then it goes high when it reaches that value again, low. So if we look in the scope, the difference between the two is like this. To visualize the different modes, I've done a simple sketch that outputs 6 random signals to each of the pins. And here we have pin 6 and 5, so that's port OC0, A and B. This is PWM speed, default PWM speed is 980 Hertz. If we were to listen to this, it would sound like this. So we are still in the default where the signal is audible. This is fast PWM. We can see this because all the waveforms. I've done a DualPWM voltage divider so we can see the difference between fast and phase correct. So in this fast PWM, you see we start at the beginning, and then depending on the values of the two PWM signals or values, they stop at different, so there's a slope going like that, just as, and going quite fast. So this is 980 Hertz. If we instead take OC1AB, so that's pin 9 and 10, that should be those two pins. We need to slow down a bit because this one is only at 490 Hertz. Still audible, sounds like this. But I would say I like this mode better because, as you can see, it is more too slow. It is more centered. So for working with analog signals, I would say this one is a nicer fit. I don't know if it really would matter, but I like this one better. And the same with OC2A and B, so that's pin 11 and 3. It should be that one, and pin 3, that one, which is also 490 Hertz. Same, and phase correct PWM. The second thing we need to change is the prescaler. The prescaler is a value that we use to scale down the speed of the microcontroller processor oscillator. So in fast PWM, for example, we have the speed of the PWM speed for fast PWM is the clock frequency divided by the prescaler times 256. And all the ports have divide by 64 as the default prescaler value. So that's 16 million then for the clock frequency divided by 64 times 256. So for fast PWM, that ends up at around 980 Hertz. As you heard before on the oscilloscope, it is in the audible frequency. Phase correct PWM speed is, as we see here, half of that speed. So the clock frequency divided by the prescaler times 510. And no, not 512. And if you wonder where those 2 extra bits go, you can read about that in the Secrets of PWM on the Arduino docs or in the datasheet. So 16 million divided by 64 times 510, which is around 490 hertz. So if we instead divide by 1, no prescaler on these 2, the fast PWM ends up at around 62,500 hertz, and the phase correct one at 32,000 something, 300 something, I think. Both of these then are out of the audible range and will work for our purposes for carrying audio and CV signals without any problem. How do you set them then? Well, all these settings are done in the timer counter control registers. And there's 6 of those, 2 for each pair, and some values is just 0 from the beginning. Some values needs to be set to 0. So these 2 and these 2 needs to be set to 0, and that one needs to be set to 0 for PWM to work. But except for that, these are, so the COM 0A1 and 0 and B1 and B0, for example, on the TCC R0A register, sets how, and yeah, this is where it gets complicated. So you can read it in the data sheet. Again, let me find it. So we have it here, and this is how these 4 bits control how the ports should handle when there is a compare match to the timer value. And you can even disconnect. If you do it wrong here, you disconnect the compare output to the pin. So therefore, I believe it is 10. 1010 is on all these registers, all the A registers you set to 1010, and that will work. Then you have the WGM, and you have 0001 and 02 on the 0 register. On the 1 register you have 1011, 12 and 13. So there's actually 4. That mean, and these are for setting the mode. Again, here you also have 3, like so. This is the mode you want to be in, and those worked in conjunction with these 4, of course. And let me just show again in the data sheet. Here we have 000 means normal. Top is 255. Update is immediate. And then we have here 001 is PWM phase correct. And top is 255. And then we don't need to discuss the other ones except fast. So we have phase correct and fast PWM. Those are the 2 modes we want, with the top being 255. I'm not going to go through the other ones. So that means that we should have 001 for phase correct or 011 for fast PWM. And this is only on TCC R0A and B, because here we have way more modes, so we need to do a little bit different settings on 1A and 1B. And 2A and 2B is the same as 1A, so there. We go into all the rest of the B registers. The 2 first bits, I set them to 0 on all 3 here, because they need to be 0 there and need to be 0 there, and should be 0 there when using PWM. So just zeros, 1 extra for the mode, and then the 3 least significant bits on all the B registers are for setting the clock. And again, in the data sheet, we can see we have a different 000 means no clock source, then the counter is stopped. We don't want that. 001 is no prescaling, divide by 1. 010, 8, and then we have all the ones, and down here we have 2 external ones. So that's basically it. If we go into the Arduino IDE and look and see how this is done in reality. So to show this, I've done a small sketch here. One of the first really important things we actually need to do for this to work is we need to set the pins as output. If we don't do that, there is an extra register we need to set that I'm not going to go through. So we set all these pins as output, and then we have the settings TCCROA, and one way of setting this, if we know exactly the value we want, then you can do it like this. You just set the register name and you set B and then the binary value that you want. So in this case we set COM0A1, COM080, COM0B1 and COM0B0 to 10, 10 and 10 for clear on compare and set to bottom. And then also we set the WGM01 and WGM00 bits to 11, and that was for fast PWM. We also need to remember the WGM02 is in the TCCR0B register, so we set that as well. But the TCCROB we set in a different way, just to show that you can use different ways. Here we take the value, we set the value of the register to the original value of the register, and we AND that with a binary value. What this means is when you AND something, let me add a few rows for that. When you binary add something, this basically, when you have a 1 in the value that you add, this means that this will retain whatever value you have at the original value. So if this is the original value, and we have for 1111 here that we write, just like we do here with 5 ones. So this will in theory turn, because it's AND, so if this one is a 1, and we add a 1, then this is AND, so this will stay a 1. If this one is a 0, the original value is a 0, then this is not AND, so that will be a 0. And then we have another 1, and then we have another 0. And then all the ones that are 0, we will actually reset to 0, no matter if it's a 1 or a 0, it will become a 0, because 1 and 0 is still a 0, and a 0 and a 0 is also a 0. So that will, doing the AND command, we will reset those values that we want to reset, to then do an OR, where we set those bits. Let me add an OR here so you understand that. So here we have an OR command then. So this value here is, I've taken this value we got over here. So then we do the OR command, and that means, so if one OR, if this one here or this one here is a 1, which is, it is, then it is a 1. If this one or that one is a 1, it's a 1, but it's not because they're both 0, so it's 0. And then that one is a 1, and then all those are 0. And then those two ones that we add over here, those will be set to 1 because we do the OR command. So we just set the bits that we want to with this command. Instead of this, we just brute force set the values we want. This one is a bit more soft in its approach. The TCC R1A I set like this because it's, well, again, you can read all what I'm doing here. So this one is a bit special because it has 4 bits to set the mode. So here we have 10, 11, 12, and 13 is set to 0. All of those two are set to 0, 1, and 12 and 13 are set to 0, 0. And TCC R1B for phase correct 8-bit. There are tons of mode for the OC1 output compare. And then finally we have the TCC R2A setting here the mode and also the Prescaler divide by 64. So basically we just set up all these commands is just to set up the PWM as it is from the start, original. So what we should do on all of these outputs, TCC, RNB registers, we should then, instead of doing 0, 1, 1, we should now do 0, 0, 1, which means no prescaler. So we do that there when we do TCC R1B and TCC R2B there. And when we do this change, you will see it goes from that we saw at 1 millisecond to this. And now we need to zoom in to around 10 microseconds. Then we see the waveform again. And as you can see, we zoomed in to a factor of 100, I believe, to just get back to where we were. And this will make it a lot easier to make a filter that smooths out these really tiny differences, just a few microseconds, and to get a good clean signal. I feel this is super difficult to explain, and if you're thinking this is fuzzy as nothing else and you don't understand, I've done this cheat sheet for how to set the registers for faster PWM speed. So if you don't want to know all the stuff that I'm talking about here and just want to set really fast speeds, then I have a link to this document as well, or you can see it here. So here you have examples for setting pin 5, 6 speeds, and you just set these values here, and here you have for pin 9, 10 and for 11, 3. So just to make it super simple for you, and if you don't want to know all this, this is the few minutes of this video that you need to see, and use this link to get just the bare minimum information that you need to set faster PWM speeds. And then we get to the second problem we need to solve, and that is the ratio of the resistors. So the formula for the least significant bit resistor equals 2 to the power of bits of one of the ports times the resistor of the most significant bits. And that means that in a 10-bit situation where we have 5 bits on each port, that would be a 30 times 32 for the first resistor. So if we have a 1K resistor for R1, we have a 32K resistor for the least significant bit R2. And as we go down 12, 14, 16, you see we just double the amount of we double the ratio every time. So for 16 bits, if you want to have 16 bits, we need to have 256 times R1 to get for the R2 least significant bits. And that's not difficult until you start to look at this little table here. So this is the resistor accuracy. And for this to be, for the ratio between the most significant bits and the least significant bits to be okay, at 10 bits, the resistor accuracy needs to be within 3%, which is quite easy. Today, the most resistors you buy is 1% accuracy. But then we go down to 12 bits, we are still above 1%. 14 bits, we are below 1%. And at 16 bits, we're at 0.39% accuracy. And this is also, this accuracy is calculated by doing 1 divided by the factor here. So 1 divided by 32 is 3%, and 1 divided by 256 is 0.39%. So how can we solve this? And we're going to look at Open Music Labs. Again, that's a really good site for anything DualPWM. I'll put the link to this site as well in the description. Open Music Labs is a really good resource for learning about dual and triple PWM even. And when we go down, so here we have this table that I showed with a 0.39% resistor accuracy. Here 0.39, 2 times 8 bits. PWM frequency 62.5 and 39% accuracy on the resistor. They have 62.5. As I said before, I'm running at 31.3. Not sure if that is going to make a difference. For now, we're just gonna go with this. And the reason this is so important is because the 8 least significant bits is so small compared to the 8 most significant bits. So it's really important that the accuracy is correct. I didn't quite make a good explanation of why the accuracy is so important. So if we take, for example, 16 bits, the first 8 bits, once we go up in the most significant bits, the highest bit in the 8 bits of the most significant bits, its value is 32,768. And compare that to the smallest value or biggest value of the least significant bits, it's 128. So if we take 32,768 divided by 256, which is the ratio and also the error margin or the needed accuracy, 0.39%, that is 128. So with just 0.39% error margin in the resistor value between the most significant bits and the least significant bits, we will get this whole small section here will be skewed so much that and the bits will be the completely wrong value just because the resistor is 0.39% wrong. So that's the reason for the accuracy of the resistors being so important. And they have this really interesting design here that's someone did. Steve Woodward over at EDN did that. You should go and read that article as well. But so many problems end up in this. So they use 3.9K as the smallest resistor. And the reason for that is because the pin on the Arduino actually has a pin resistance, output resistance of 40 ohms. And that means at 3.9K we are already at a 1% error ratio here, because 40 ohms from ish 4000 is 1%. So maybe that's why they have 3.9. So you add 3.9 and you add the 40 ohms, so you get closer to 4K, which is then the bigger resistor is 1 mega ohm. If we look at the, let's look at the small, like here. So this would be 3.9K R1 and R2 would be 1 mega ohm. Just this simple voltage summer. The second resistor would basically be 3.9 times 256, so not even 1 million. I'm thinking we can do this if we just add a pad where we can add a bunch of smaller resistors, like one 3.9K, one mega ohm, and then a bunch of maybe 1K, or so we have 1 or 2 extra slots to add and tweak the resistance a bit if we're using 3.9K. And again, I guess we need 2 if we're gonna run 16 bits, because 1K and the 40 ohm on that's 4% already, so that will not be very correct in the ratio. We could also build this circuit, and you can read all about this circuit here on this page. It is genius in many ways, but I think it's a bit overkill, and I just hope we can get it as close to 1 to 256 ratio as possible. And as I said in the beginning, we are going to stop here because I think you've got enough information, and I think you need a good night's sleep to process all that. I'll get back with the next video about the filter design for this, or one of many filter designs you can do, I guess, but my findings on doing that. So until that video, hope you like this one, and yeah, see you in the next one. Take care. Bye.